Tokyo University in Japan. So firstly, I would like to thank all the person to come here, especially I appreciate Tenkoba Sensei to make this opportunity. I'm very glad to be here today. So today, I would like to talk about mathematical modeling of phenomenology. I'm not sure. Okay. So my major is system identification and signal processing for noise removal and biomedical signal processing. And it seems to be different all of them, but common technique is mathematical modeling by equation using self-tuning identification method. This is my original, the self-tuning identification method. So today's topic is EEG modeling by the various cases with heavy noise. We call the Kansei modeling. The Kansei is Japanese word because studied first in Japan. So Kansei is similar to emotion and sensibility, but totally different. Emotion and sensibility is innate ability, but Kansei is acquired afterwards, so totally different. How I feel, this is Kansei. When I see something visual stimuli, it seems beautiful and comfortable. This is Kansei. So we focus on this Kansei using EEG. EEG is action potential measured from the scalp. The detected data is translated to the frequency domain. In the frequency domain, 0.424 we call the delta wave, and 426 we call the theta wave, and 7 to 14 we call the alpha wave, and 14 to 26 we call the beta wave. So EEG is very small, and unit is microvolt. So this is very noisy, and there are many noise factors. For example, the environmental factor, and the electrical factor, and the EMG factor from the muscle. We consider all of them factor. So when we use the EEG. And by the way, around here, millions of neurons are included in the cerebral cortex. So actual state of physiological phenomena is membrane potential, and which is caused by the non-uniform difference and by the action of molecular pump. So this is equilibrium potential of ionics, and they express this equation. And this equation shows the potential difference of 58 millivolt occurs at a concentration ratio of 10 times, like this. So in general, K, Na, and Cl has contributed the membrane potential of neuron and expressed by this equation. So in steady state, K ions are dominant, but transient phenomena occur due to ion fluctuation. The pulse signal generated at this time is action potential of EEG. The actual state of electrical phenomena is the membrane potential like this. So EEG can be acquired by setting the electrode inside and outside, and same if original, and measuring the potential difference between them like this, from here to here. So, but it is difficult to put on the inside we call the implant type. This is very difficult, and generally we put on the scalp the electrode. So we can replace the state of this electrode on the scalp with an equivalent circuit. This is equivalent circuit model, EEG detection on the scalp. This is a equivalent circuit of EEG. So we can replace this equivalent circuit like this second order model. We can rewrite this second order model. This is a continuous time model. So this equivalent model is made to know the order, just made you know order of continuous time model. So we apply the former, the second order model to a real open loop system like this, that we construct the pre-filter for the noise reduction, and we define this function and this transfer function, and this is produced by the discrete time model like this. And this term means the second order model from the equivalent model. So for the making a mathematical model, so we consider this augmented system. This is a new transfer function from the augmented model. Please note that this is a discrete time model, the first term, and the second term is a continuous time model. And then we calculate this term to rewrite by the Paddy approximation like this. So we can rewrite this term like this. Okay, understand? So we can rewrite this term like this. So furthermore, we rewrite by the Z transformation, we can rewrite this new transfer function like this. So this is an augmented model. So this is an augmented model, the former calculated. So we define the alpha of Z inverse and beta of Z inverse like this function. So alpha 1, alpha 2, beta 0, and beta 1 is calculated by these equations. And coefficient A1, A2, B1, B0 is calculated by this recursive least squares algorithm like this. So we can estimate these parameters. So we can obtain the augmented model. So this is a self-tuning identification method out of them. So we apply the self-tuning identification method to a real stress modeling. This is EEG data repeating the stress. This picture shows the Azuki experiment. He moved the small beans tray to tray for 1 hour. And from the 15 to 60, we adopt the stress model, stress data. So we gather this kind of data for 70 years, and the total, the 8,000 data. So we construct for this data. On the other hand, we use the simple EEG devices like this. In the world, there are many simple devices, like, for example, like this. So, but this is very noisy. So we investigate 62 kinds of devices of SN ratio like this, but we can find that almost of devices are noise devices. This is too complicated. And one of them, this is a mental training system using EEG. So this is produced by the Brain Function Research Center. They say that they can obtain the concentration ratio and the depression. But we don't know what is a concentration, what is a depression. This is a very important problem. So they say that they can obtain by using the threshold method, just the threshold method, using the beta wave. So the signal analysis is not enough. Next one is EEG mouse. This I think it's a very interesting devices, but detected data is not EEG but EMG. So for all goods, the EEG signal analysis is not enough. I'm often asked to various persons what device is the best. My answer is anything. So our skill is signal processing, and if raw data can be obtained from the devices, no matter what devices we use. the same result can be obtained. Our novelty is signal processing, and they are structured by the 17 years data per one situation. For example, the stress data and the concentration data and so on. So this is a mathematical model from this augmented system. So we calculate this kind of the data. This is a stress model, and the concentration rate here, and the sleepiness here, and so on. So this is our pattern. So we apply this kind of equation to a real product we call the cancer analyzer. If you use the cancer analyzer, you can see the cancer online manner. So I can demonstrate from now on. So please change. From the he detected. Sorry, we measured his EEG. Okay, please. Please come on. No way. Okay. Okay. We measure his EEG and measure his cancer. That this is interest, like, concentration, and stress, and calmness. So we can see his stress now. Sorry, this is the noise detection and the noise reduction here. And you can see his stress like this. Very no alarm. This is all of them. The blue line is stress, and the yellow line is interest, and the red line is like, and so on. You can see his cancer real time. Okay. Okay. How about you?
Very sorry.
Okay. Very noisy. Very sorry. His stress is going up. Going up here. This is here. Okay. This is our product. Okay. So thank you so much. And next one. So please change. Please change the. Thank you so much. Okay. We introduced our real product by the NHK World News. So please show the movie.
A Japanese professor has come up with a new technology she claims can read minds. She says the brainwave analysis system will help businesses better understand their customers' needs. Workers at a major restaurant chain are testing a menu item that is being developed. This device measures brainwaves from the frontal lobes of people who try the product. An application analyzes 5 feelings: how much they like something, and their interest, concentration, stress, and sleepiness. The new menu item is a cheese souffle topped with kiwi, orange, and other fruit. The app checks the reaction of a person who sees the souffle for the first time.
Please open your eyes.
Okay. No way.
When she sees the souffle, the like and interest feelings surge on the graph. This proves the dessert is visually appealing.
Okay.
Now, please try it.
Okay. So let's go. Okay. Okay. Sorry.
A Japanese professor has come up with a new technology she claims can read minds. She says the brainwave analysis system will help businesses better understand their customers' needs.
Workers at a major restaurant chain are testing a menu item that is being developed. This device measures brainwaves from the frontal lobes of people who try the product. An application analyzes 5 feelings: how much they like something, and their interest, concentration, stress, and sleepiness. The new menu item is a cheese souffle topped with kiwi, orange, and other fruit. The app checks the reaction of a person who sees the souffle for the first time.
Please open your eyes.
When she sees the souffle, the like and interest feelings surge on the graph. This proves the dessert is visually appealing.
Now, please try it.
After the first bite, the like level goes up to 60. That shows she likes how the dessert tastes. After another bite, the like level reaches 80. She really enjoys the taste of the souffle. It scores high in terms of both looks and taste. But there's an unexpected problem. When she tries to scoop up the fruit, the stress level soars to 90.
I didn't know where to put the spoon. I felt it was a little difficult to eat.
It turned out it was difficult to scoop up the fruit with a small spoon. So people at the restaurant chain are thinking of serving the souffle with a fork instead.
With the device, we can measure emotional changes in minute detail in real time.
This is a printing and design firm in
This
Tokyo.
is our product, one of them. And then, now we are going to detect the like and dislike, and in concentration, interest, and stress, sleepiness, and continue, and like, comfortable, uncomfortable, unpleasant, relaxed, devotion degree, and the addictive, taste, lighting, comfort, satisfaction, and achievement. So our product selected the World Innovation Best 50. So in conclusion, we propose a new method to qualify the human concept by using EEG with real-time noise reduction and make a mathematical model. So please note that all phenomena is indicated by the differential equation, even though it is Aquaphotomics model. So this is my philosophy. That's all. Thank you so much again.
Thanks for your talk and for having kept perfectly the time. So we have time for at least 2 questions. So please.
My question is connected with application applied the theory of Padé approximations. This means you represent a function
Yeah. Yes.
in a
Just,
rate of 2 polynomials. But
Yeah.
in the theory of Padé
approximation
Yes.
here. Okay.
must give the consideration to election of the highest power
Yeah.
of the polynomial.
Yeah.
First.
Yeah.
Secondly, the meaning of singularity of the approximation. This means the zero of denominator
Yeah.
of the polynomial of
Yeah.
And second, question connected to the brain waves. Do you have some idea how to arrive to idea to not to reduce the noises of but to increase? This is so-called brainstorming, very largely used in some scientific research.
Okay. Good question and good comment. This is a Padé application, first order Padé application, but we try to the second order, the third order, but this is very good. The experimentally we used experimentally. And the second person that we use the many times of the EEG, so that we apply to many kind of the situation. So we try to remove all of them, but the SN ratio is going up. So we calculate the SN ratio of one of them. So we try to again and again. So we tried. Thank you so much.
Okay. Just very quick,
Oh, okay.
but really quick.
I'll try to be quick, but still super interesting presentation and wonderful demo. So still two questions, both really quick. The mathematical equation that you show is the weighing factor. It's been
Yeah.
okay. The second question is how to quantify
Quantify.
those stress or happiness or
Yeah.
or whatnot. Thank
This
you.
is from the 8,000 person, the average, the 50% going to 50%. So after the average is going, if the stress is average is upper, so this is going up.
One last quick one, sorry. So for individual use, do you have to establish a baseline first in order to use it properly, or it's not necessary? Thank you.
Yeah, and we try to use the average. The firstly average, we measure the average. The firstly, yes, baseline.
Okay, so thank Professor Mitsukura once again.
Thank you so much.
And the next speaker is Dr. Harigahani from Haunier. And